Hi guys, this is a pre-calculus level lesson called forced factoring to help with the limit. Let's take a look at a problem. I'm writing the limit as x approaches infinity of x minus 2x squared all over 5x cubed minus 7. We have a rational function. This is an infinite limit. What do we do with this? Well, in a previous lesson, we talked about dominance. We talked about how fast the terms of an expression go to infinity. And in this case, we can definitely analyze this with dominance. There are 4 terms here. 5x cubed is going to infinity. Negative 7 is constant. It's not going everywhere. It doesn't change or grow. It's negative 7. The x term goes to infinity. And the negative 2x squared also goes to infinity. If we were to take a look at these terms, 3 of them going to infinity, 1 of them is a constant. What's the overall limit? It's confusing. So which one is growing the most quickly? It's this cube that dominates this linear piece, this quadratic, and this constant. The 5x cubed is growing so fast as x goes to infinity, you can think of it as overwhelming the other terms. And that term has the influence on the final limit calculation. This expression, when we consider dominance, is like the expression 1 over infinity, because the term in the denominator is the one that we would consider growing, overwhelming the others as if the other terms were like 1 compared to the 5x cubed growth. We have a limit law. The limit as x approaches infinity of 1 over x is equal to 0. I'm going to put a box around this because this is special. This is a theory of mathematics that's been included. We can rely on this. And notice in this situation, this limit law is like the situation we have in this problem, so we can look to it to consider what's happening to 1 over that dominant term. The whole thing is going to 0. 0 is indeed the answer to this original limit question. But the way that we found this limit using the concept of dominance is not formal. Dominance is very helpful when trying to find infinite limits, but it's not formal justification. So we're going to go a little further in this lesson and start to talk about how we would not use dominance, how we would use formal justification to find this limit. And to prepare for that, and the meaning of it being formal, is that it relies completely on limit laws. This limit law helped us understand this situation, but there are a couple more limit laws that we're going to use formally, and I'll remind you of them here. The limit as x approaches infinity of x is infinity. Put a box around it because it's special. And the limit as x approaches infinity of any constant is that constant. These limit laws should be fairly obvious. You'd want to memorize them. Let's apply them to this problem. Now, before we can take the limit, we still have the original complication here. We have all these terms going off to infinity, and we have one constant term. But I could use some algebra in order to change this rational function. And the algebra that I'm going to use I call forced factoring. We know what it means to factor. It means to take out a common factor of the terms and place it outside as if we're creating a distribution problem. The reason why I call it forced is because what I'm going to choose to factor out may not begin as a factor of the term. That's okay, as long as we keep track of it mathematically. I'm going to choose to factor out an x squared from both these terms in the numerator. Well, factoring out an x squared from the negative 2x squared term is fairly obvious. If I factor out the x squared, it would be like what's left after I divide this term by what I factored out. And what's left of this term is a negative 2. But what about the x? The x has just itself x as a factor. If I factor out x squared from x, I'm going to have to force one extra x out of it. That's okay. The result is 1 over x. Why? Well, I could check by redistributing. 1 over x is what remains after I divide x by x squared. I can check it by remultiplying. X squared times 1 over x is the same thing, x squared over x. One of the x's cancels out, leaving the second x in the numerator. So I have forced x squared out of the x term. Okay, I'm going to do a little bit more of that. I've got a 5x cubed minus 7 in the denominator, and I am going to force x squared out of both those terms. You don't have to technically force it out of the 5x cubed because there's an x squared factor already there. What remains out of 5x cubed when I divide it by x squared is 5x. Nothing special. What remains out of this negative 7 when I divide it by x squared? Well, the result is going to be the negative 7 divided by x squared. The x squared wasn't there to begin with, but if I include it in the denominator, then that is the result after I factored out an x squared. And you can check by remultiplying to see if it recreates what you started with. Okay, why would I do this? Well, this is still a limit as x goes to infinity. But if I've factored out an x squared from both the numerator and denominator, I can now algebraically cancel them. And I get the equivalent expression, the limit as x approaches infinity, of 1 over x minus 2 all over 5x minus 7 over x squared. Why is this better? Looks more complicated. But every one of these terms, I can now use a limit law and take the limit of the entire thing. If I took the limit as x approaches infinity of every single piece, the limit laws would give me an answer. Let's take the limit of 1 over x. That's one of our limit laws. It becomes 0. Let's take the limit as x approaches infinity of this constant negative 2. This limit law says it's going to be negative 2. Over. Now in this case, I'm taking the limit as x approaches infinity of the product of two things, a constant and x. So it's going to be the product of those two limits. The limit of the constant, which is 5, and the limit as x goes to infinity of x is a limit law, infinity. Carrying on, I get minus, taking the limit as x approaches infinity of 7 over x squared, is actually thinking of the product of three things: the constant 7, a 1 over x, and a second 1 over x. 7 over x squared is the product of a constant and 1 over x and another 1 over x. That's three applications of the limit laws. We know that the constant is going to remain the constant, multiplying by the limit of 1 over x, which is 0, and the second 1 over x. Notice if I draw this next line of work, I've taken the limit of everything, so I don't draw the limit out in front here. I've taken and applied the limit to every one of these pieces. This is the result. But because I'm using infinity in here, This is technically not equal. I'm going to use the approach arrow. Infinity is not a value. So if it crops up and you want to show it like that as a concept, that's fine, but we're not technically equal to this yet. We're almost finished taking this limit formally. Let's wrap this up a little bit. 0 minus 2 is a negative 2. And then we have, no, I'm not going to use the equals because I'm still going to use the infinity here. 5 times infinity minus 7 times 0 is 0. I wouldn't have to draw minus 0 if I didn't want to. And finally, we can apply the equal sign because we know that we are thinking of this as a negative 2 over 5 times infinity. The negative 2 and the 5 are not going to matter with the magnitude of infinity. And this is, like the limit law, 1 over x is equal to 0.